Our first speaker in the next session is Matt Brecknell from Kry10, who knows a lot about verification because he was also in the seL4 verification. And he's going to tell us about a programming logic for system verification.
So what that means is we want to verify properties of systems of user space applications running on seL4. Up to safety properties like functional correctness and integrity style security properties. So this work is part of the Converse project, which is a partnership between Proofcraft and Kry10. It's funded by the German Agency for Innovation in Cybersecurity as part of their program Ecosystem of Formally Verifiable IT. Cyberagentur is represented by Christian today, and Christoph Hoff will be giving a keynote on Friday morning. Before we can talk about what it means to verify a system, I want to clarify what we mean by systems. And in our case, we have an seL4 microkernel running a number of user space applications. Those user space applications can make invocations to the seL4 kernel and also requests to memory. Like David and the neutrality project, we actually want to run a multi-kernel configuration with a separate instance of seL4 on each core with partitioned kernel memory. But there's also some global memory that is accessible to apps across different cores. And so now user space applications can make requests to their local instance of seL4, but can also make requests to a global memory. User space applications can also talk to the outside world by making reads and writes to memory mapped I/O ports, and also to receive interrupts via the kernel. So to define the system, we can essentially draw a box around what's inside the system. And there's a sense in which we don't really care what goes on inside the box. What we really care about is the interactions on the boundary of the box. So those reads and writes to the I/O ports that talk to the outside world. Of course, we do actually pay attention to what goes inside the box, but mainly for the purpose of convincing ourselves that the things that go on inside the box give us exactly the observable interactions that we want. And on the way to establishing that, it's often useful to draw boxes around subsystems. So in this case, we'll make a subsystem of each CPU. And so that subsystem contains one instance of seL4 and a number of applications. Those invocations to the seL4 instance are internal to that subsystem, but the requests to the global memory are observable events for that subsystem. And so the key ideas are that we have a notion of composition, and at each level of composition, we can consider the interactions that are internal to that subsystem and those that are externally observable. Cool. Now, before we talk about what it means to verify that, let's just do a quick recap of how the seL4 verification works, because there are some nice things about the way this is done that I want to replicate. This is a simplified version of the picture that Gerwin showed earlier. We have several specifications at different levels of abstraction. We start at the bottom. There's a very detailed model of either the C code or the machine code. And so this has to deal with all the complexities of that programming language or machine. Moving up to the design level, we have a specification that uses all the data structures of the implementation, but gets rid of all those annoying details of the implementation language. And going further up to the abstract specification, this still looks like a program, but it's using very abstract mathematical structures that kind of remove some of the details of the implementation data structures. So there's, I think, three things that I want to take away from this. First is the idea of writing specifications as programs. This is nice because it gives a separation of concerns because we can still prove properties about the specification, and those transfer down to the implementation via the refinement. In fact, we can prove multiple properties about the specification and do that more easily at the abstract level than we could at the implementation level. So this kind of proof of refinement between an abstract program and an implementation gives us that nice separation of concerns. We also get a nice separation of concerns between the levels of the refinement, because the top refinement between the abstract and the design just talks about the data refinement between the abstract mathematical structures and the implementation data structures. And then the second refinement can just deal with all the technicalities of the implementation language. What was the third thing? I forget the third thing. All right, yeah, so the first two specifications, the abstract and the design, we use this idea of a monadic shallow embedding. It's just a state monad for those who are familiar with Haskell. And the nice thing about this is that we can just use the expression language of the host prover. We don't have to decide what operators we want in our specification language. We don't have to prove theorems about substitution. We just use the expression language that's there. So this makes it very easy to write natural specifications that look like programs. Okay, so moving up into user space, we have a system of many apps, and we can kind of replicate this structure for each app. We have an abstract description of an app, its design, and its implementation. But if that's all we do, then we just have a collection of program verifications. We don't have a system verification. So we need one more layer above this that describes a specification for the system, and we do a refinement proof to show that that collection of apps somehow implements a system specification. So that's kind of the goal. There's a typical recipe for doing these kinds of verifications. You obviously need a language to write your specifications, and then you need to say what those specifications mean, so that's the semantics, and you need a program logic for actually doing the reasoning steps. The idea is that when you've proved something in the program logic, this tells you something about the way a program executes in that semantics. We're making a slightly different choice to some other people in the room. We want to build our program logic on an existing concurrent separation logic, because we need something now. And there is like a very capable separation logic called Iris. Yeah, so we plan to build on top of that. We also want to use interaction trees. Now, this is becoming more common for describing semantics of things, but slightly more unusual use is that we also want to use them to write specifications. The reason for that is because it gives us that shallow embedding. Cool, okay. Let's first look at what specifications look like. And so this is a made-up, very simple system. We're just going to add some numbers. So we start with an adder process that has a receive capability on an endpoint, and it just receives something, replies with the number that it sort of kept in its head, and then starts again, adding in the number it received. Now this adder definition here is an interaction tree. I'm not going to talk about exactly how the concept of interaction trees are defined, but this is an interaction tree that describes a process. And it's an abstract description of an application, a user-level application. Yeah, and it gives us a very natural way to write specifications. In particular, the X at the end of the arrow, that is just an ordinary binder in the host prover language. And that expression sum plus X is also just an expression of the host language. Yeah, so we don't have to decide ahead of time which operators we want in our language. So what does this mean? So there's a couple of things in there that indicate seL4 invocations. The EP receive is a receive on an endpoint. But as far as this specification is concerned, it doesn't tell us anything about how endpoints behave. The EP receive is just syntax. It's just like a data type on the right. Details don't matter. But there's nothing there about how endpoints work. This also gives us a nice separation of concerns because we're describing how the adder process behaves, but not how seL4 behaves. That comes later in the semantics. So we can build out our system with another process that sends values into the endpoint, and it reads something from an I/O port, sends it to the endpoint, gets an answer, and writes it back to the I/O port. Really simple system, but it's just enough to describe what we want to do. Once we have these two processes, we can then think about, well, what is the system? And we can draw a box around the things that are inside the system, and then identify the thing that's at the boundary, and that's the I/O port. And we can describe in another specification how that I/O port should behave. And you can see that the specification there has some bits that come from the client, some bits that come from the adder, and then some things like the call and the receive and the reply are handled internally. And ultimately what we want to prove is that somehow the parallel composition of those two processes refines the specification. Okay, so that's the goal. Cool, so that's a bit of a picture of what the specification language looks like. It's shallowly embedded. It allows us to describe processes at a very abstract level and also describe specifications of the system. But now we need to give meaning to those specifications, and so we need to define what system states look like and then how executions run from those system states. This is sort of the aggregation of what a system state looks like. A system is just some memory and some CPUs, and each CPU has some threads, endpoints, and some other things. We can describe this structure as a bunch of records. So a thread is just an interaction tree that emits thread events. It also has some capabilities and other things. But yeah, the interaction tree is the key thing that describes the behavior of the thread. Now these thread events will include things like seL4 invocations, reads and writes to memory and I/O ports. I think that's about it. And then a CPU state is essentially the state of an seL4 instance. So it has a collection of threads, a collection of endpoints, and some other things. And finally, we can consider a system as a collection of CPUs and some memory and some other things. So now once we've described the state, we can define how the system executes from some initial state. And we can do this at both levels of composition. So run CPU takes an initial CPU state and then describes as an interaction tree like a trace of CPU events. And those CPU events will be the things that are externally observable to a CPU, which will be things like memory reads and writes and I/O operations. But the seL4 invocations are handled internally by that run CPU. The other thing this run CPU has to do is interleave the steps of the threads. So this is not a small function because it essentially encodes the entire semantics of seL4. As a consequence of this, we clearly have to write another specification of seL4. I think as Dave was alluding to, this seems like we need to do this anyway just to understand how to verify systems on seL4. Once we have these two specifications, then hopefully we'll be able to see how to build a bridge between them. And finally, run system does the thing at the next level of composition. It interprets those memory operations, interleaves the CPU steps, but exposes the I/O operations in the trace of system events. one nice consequence of describing the semantics as interaction trees is that these are actually executable specifications. In principle, we should be able to actually extract a runnable program from these specifications to simulate a system. Cool, so that's a high-level overview of what the semantics would look like. And finally, we need a program logic to actually reason about these systems. We'll build this on Iris because it's a very capable existing concurrent separation logic. Fortunately, Iris is very modular, so it has a bunch of things that we can use, but there are some things that we can't use. It comes with a language framework that allows you to define a programming language and then get a program logic for free, but there are some limitations to the kinds of languages it can describe. In particular, we can't describe processes that block, and it's not very well suited to describing processes that emit events. Okay, so there's some new things we'll develop. The ways of using specifications as interaction trees and a program logic based on that. But like most separation logics, we will have a range of sort of ownership assertions, and these assertions do two things. They assert some fact about a piece of the system state, but they also assert a kind of ownership that we have the exclusive right to interact with this object. And that's very useful for concurrent systems where you want to know that some other thread is not interfering with what you're doing. Most of the time, when you're doing a proof, you're proving a weakest precondition assertion. So the weakest precondition asserts that we have exclusive ownership of the resources needed to execute some threads safely. So a quick picture of what this looks like. If we want to prove that we can safely execute that adder process, we want to prove that we have the resources to execute that thread. The first thing we need to know is that we have a thread points to assertion that says that we own the exclusive right to execute that thread and that this is the program we're executing. The first step of this program is to perform an EP receive, and so we also need ownership of the slots, the endpoint and the reply slot. So we have some ownership assertions for the slots. And one of these slots contains an endpoint cap with a reference to an endpoint object. So clearly we need some ownership of the endpoint object. Now this is only a temporary ownership because things like endpoints are meant to be shared between threads. And thankfully, separation logic has some mechanisms for doing the sharing and enforcing protocols for accessing shared objects. But yeah, we won't go into that. But for now, for this particular step, we have temporary ownership of that object. We can take a step in the proof, which essentially performs a symbolic execution of a step. And you can see that we've reduced the program to peel off that receive operation, and the states of the objects have accordingly changed. You can see how the contents of the queue have moved to the reply cap and the continuation of the thread. So the final piece of the puzzle is how we prove refinement to some system from some system spec. And the idea here is we want to show that the visible events of the system are just the visible events that are possible in the specification. To do this, we introduce another kind of resource assertion, an IO spec, that is given by an iTree program. So specifications are also given by interaction trees. And yeah, we can see roughly how this looks. This time we want to prove that the client is safe to execute. And Again, we need thread points to assertion to say that we have the exclusive right to execute that thread and that we know what program it's executing. It wants to perform a read on an I/O port. So we need ownership of that slot, and that slot contains a cap to an MMIO object. Let's just pretend that exists for a minute. And of course, we need ownership of the right to perform operations on an MMIO object. So these are a bit different from the kinds of assertions we've seen before, where the assertion tells us about the state of something, but we don't have a state for MMI objects. We just need the right to perform an operation. So that's what we use this IO spec resource for. Then if we take a step, we can see that we reduce both the program we're executing and the specification that allows us to take that step. And yeah, the hope is that from this, we can actually obtain a simulation relation. Not 100% sure we'll get that, but we should at least get a trace inclusion, which is what we want for refinement. Cool, so that's an overview of the 3 things we need to do the kinds of system verifications we want to do. So just a few closing comments. This is a fairly fresh design. We're currently implementing the semantics and the logic for a simplified model of seL4 with just a few different object types. And as we've kind of developed the approach, then we'll build out sort of the more complex parts of the seL4 model. There's a few things I did not talk about. How we connect the 2 processes together and how they coordinate the usage of that endpoint. Separation logic has these mechanisms called invariants and ghost resources that allow us to reason about that and enforce those protocols. I didn't talk about how we're going to prove properties in the presence of untrusted apps. The essential idea there is to parameterize the entire verification over the untrusted apps so that once you've proved refinement for the system, you know that that refinement holds no matter what those untrusted apps can do. And finally, we also need to deal with non-determinism and failure. The system itself is non-deterministic because different scheduling decisions can lead to different traces, and sometimes you need to reflect that non-determinism in the spec. And failure, we just want to be able to prove for trusted programs that they don't crash, or that they don't execute invocations without the right capabilities. And so we need a program logic that can enforce that. Finally, a note on scalability. Clearly, the example I showed here is very simple, and the program logic is a little bit simplistic at the moment. But I think we have the right tools in a concurrent separation logic that allows modularity in several dimensions. And the use of abstraction in the refinement stack, I think, will also help us with scalability. Cool. Thank you.
Thank you, Matt, for staying on time. We have time for some questions.
Hey,
Dave.
So, yes, very cool. So one thing so you have an interleaving semantics.
Yes.
Is that going to be enough in multi-core? Do you don't necessarily get serialized?
There's a few interesting things that happen. I believe that there should be a reduction argument that should be generic. I don't know what that will look like or how we would prove that, but
It's likely to be in practice. I mean, there will be cases where in principle it's not. Maybe it doesn't happen.
so.
It's too much time trying to think about it.
Oh, one nice thing I think about this model is that in the run system that interprets the memory operations across cores, you could in principle plug in different memory models. Like you might start with one where it has like a race detector and just emits a fail event if there's a race. And so that way you have to prove that you've synchronized on some seL4 object. And then later on, you could actually plug in a... Yep. Another little detail of the spec language is that something like the EP call is not actually atomic. I want to make it look like the client process can't see any state in between the call and the reply, but it's actually two events in the semantics, and that needs to be exposed in the program logic. Because you say couldn't open invariant over the call because an arbitrary amount of stuff could happen in between. So I mean, yeah, like I said, just now, in principle we should be able to plug different memory models into the run system semantics, because that's where memory models matter, because that's interpreting the memory events that happen across cores. Currently, yeah, we're not really considering weak memory. I think initially we would just use a race detector to prove that, yeah, we've synchronized. But yeah, remains to be seen whether we can sort of modularly lift the different semantics into the program logic. Yeah, we'll see how that works out.